my name is Audrey Suh, and this is my Lab 3 report, The Magnetic Field of a Bar Magnet. To give you a brief introduction to this lab, the purpose of this lab is to measure and observe the magnetic field created by a bar magnet and then determine its distance dependence for on and off-axis magnetic fields. Another purpose of this lab is to give us a better understanding of magnetic fields through the use of our phone to get a visualization of the values that we measure and then calculate ourselves. Some fundamental principles that we go over in this lab are the Biot-Savart law, distance dependence, and magnetic fields. So when initially finding the measurements for this lab, I used my phone to measure the magnetic field at various locations. Then I took the x component found of the magnetic fields and then plugged that and their respective distances into their spreadsheet. From there, I was able to find distance dependence, and then I used the Biot-Savart law to calculate magnetic dipole moment. The table above is for the calculation of the off-axis magnetic fields. The graph to the right is the log of Bx versus the log of r. The line found in the graph to the right will be important for calculating distance dependence and magnetic moment. The slope and y-intercept are averages of the distance dependence n and the log of k, respectively. For our calculations, I used the slope found earlier in the spreadsheet and found that n, or the distance dependence, was negative 3.1708 meters. From there, I set the y-intercept, which was negative 15.129, as the log of b and rearranged the Biot-Savart law equation to find mu naught. From there, I found the e to the natural log of b and set that equal to the constant mu naught over 4 pi times 2 times mu over r cubed, where r equals 1 and e to the log of b just gives us b, and from there found that the magnetic moment mu naught was 1.35 amps meters squared. For off-axis calculations, we found that d is equal to 0.257 meters and that the magnitude of the magnetic field was 5.35 e to the negative 0.5 teslas. Some observations to note is that when the magnometer is far away from the magnet, it measures a near zero magnetic field in the x direction. And as the magnometer moves closer to the magnet, the measured x component of the magnetic field increases. Here are some snapshots of the code that I wrote up. On the left, you'll notice that the code given there calculates the magnetic fields both on the axis and perpendicular to the axis. On the snapshot of code to the right, you'll notice that we find the magnetic field arrow 45 degrees from the axis. These are the computational models that we found after plugging in the code. If you'll notice, the purple arrows are the magnetic field arrows that are on the axis of the bar magnet. The blue arrows are the perpendicular arrows, the arrows of the magnetic field perpendicular to the axis, and the green arrow at the top right is the magnetic field found 45 degrees off the axis. As you can see, the distance found is 0.257 meters, and the magnetic field at 45 degrees at distance d is 3.95 e to the negative 6 in the x direction, 1.19 e to the negative 5 in the y direction, and the value 1.25183 e to the negative 5 is the magnitude of b. When comparing our code calculations versus our spreadsheet calculations for the off-axis magnetic field, I found that the calculations for the distances were virtually the same. They were both 0.257 meters, but for the calculations of B net for the spreadsheet, I found that the B net was 5.35 e to the negative 0.5 teslas, and that the net B from the code is 1.25183 e to the negative 0.5 teslas. This is something to note, that the distances of the magnitude of the magnetic fields were different values despite having the exact same distances. For this lab, we were asked some questions to answer in our conclusion. What if you hadn't oriented your experiment to compensate for magnetic north and had instead laid out your meter stick at some intermediate angle with respect to Earth's magnetic field? how would our results have changed? If we hadn't oriented the experiment to compensate for magnetic north and had instead laid out our meter stick at some intermediate angle with respect to Earth's magnetic field, then the results would have been skewed because it would have also accounted for Earth's magnetic field and not just focused on the magnets. By compensating for magnetic north, we ensure that the x component of the magnetic field starts at 0 and not a different value. So we only focus on the magnetic field of the bar magnet. If we were to stick two identical magnets together end to end and run the experiment again, what would happen? What would change? The magnetic field that would be found would be stronger, but would not entirely be twice as strong because of the difference in distance. Thank you for listening, and I hope you enjoyed my presentation.